In this lesson, we're going to get an introduction of what primary trigonometric ratios are and how we can use them to find missing side lengths in triangles and missing angles in triangles. So to understand trigonometric ratios, let's start by finding two triangles with angles 90, 30, and 60. So to do that, let's start with an equilateral triangle. We can start with an equilateral triangle because we know what all the angles are inside of an equilateral triangle. We know that they all have to be 60 degrees since the angles in a triangle have to add to 180. And 180 divided by 3 is 60 degrees. So an equilateral triangle, as a reminder, will have equal sides, therefore all equal angles. So if all of these are 60 degrees, if I were to draw a line down this triangle, now we're cutting the 60 in half, and now this is going to be 30 degrees. So here's our triangle that has 60 degrees, 30 degrees, and 90 degrees right here. So we can transfer these degrees over here. So we know that this top guy here is 30 degrees. This bottom guy here is 60 degrees. And we know this guy is 90 degrees. So we'll just do our little corner. Let's come up with some side lengths that would work. So think of side lengths that you'd like to use on our equilateral triangle. Maybe you think of 1. We could use this is 1, this is 1, this is 1. So let's add in those side lengths into our triangle on the right. So our triangle that has a 60 degree, a 30 degree, and a 90 degree, that's the goal. Well, we know that this side here corresponds to this side here. So this side must be 1. How about the bottom side here? It should be half of this guy. So this bottom should be 0.5. So I'm going to put 0.5. And how about this side length? So we don't have the height of this triangle, but we can find the height of the triangle because we know this is a right angle triangle, so we can just use the Pythagorean theorem to find this guy here. So let's say if we call that b, we have a squared plus b squared is equal to c squared. I know what my hypotenuse is, it's 1, so 1 squared has to equal, my a is 0.5 squared, and then let's solve for b squared. So simplifying, we have b squared equals 1 squared minus 0.5 squared. And then we're just going to square root that. And we get this decimal. We get 0.8660. So we'll just put 0.8660. So that's what this side length is, 0.8660 approximately. So now we have one triangle that has the angles 60, 30, and 90. We've derived it. Now let's come up with a second one. That's what we're being asked to do. So can we do the exact same thing? Well, we know what all the angles are again. We know that this is going to be 60. If we do a line down here, we know this is going to be 30. Let's come up with a new side length. So instead of 1, maybe we use 2, or maybe we use 3. Why don't we just use 3 as different side lengths here? So if we fill in everything here, we know this guy up here is 30 degrees, this guy up here down here is 60, then we have 90, and this side is 3. This side here is going to be half of 3, it's going to be 1.5. And this guy here, well, we just got to use the Pythagorean theorem again. So we have our a squared is 1.5 squared plus b squared has to equal 3 squared. Solve for b, and we're going to get the square root of 3 squared minus 1.5 squared. And it equals 2.59807. So we can just put 0.1 approximately. So this guy is 2.59881. So now we've made two triangles with the same interior angles. So these two triangles are called similar triangles. Similar triangles have the same interior angles. And there's something special that they all share with their side lengths. So one property that's similar is that there's a relation between 1 and 3, these two numbers here, and these bottom numbers here. Can you figure out what it is? So play around with your calculator and see if you can figure out what the relationship is between the side lengths of the corresponding sides in the triangle. If you're back at the video, hopefully you've tried to figure out a pattern between these corresponding sides. And if you try dividing them, then you're going to notice a pattern. If you take 1 divided by 3, you would get 0.333333 repeatedly. And if we take the bottom sides and divide them, 0.5 divided by 1.5, you get 0.333333 again. Even when we take these two, we get 0.333 and then some other numbers. So it doesn't keep going 3333333, but notice that we also estimated those. We rounded them. So these aren't perfect values either. So every time we divide one corresponding side by another, we get this same value. It's 0.333, which means the ratios between the corresponding side lengths are consistent. So we can just divide every single side length by 0.333 and get all of the side lengths here. Or alternatively, we could just divide all of these by 3 or multiply them by 0.333 and get all of these side lengths right over here. So there's another way we can look at this pattern. Instead of looking or look for a pattern, instead of looking for a pattern between these two, let's find a ratio that's in this triangle and also in this triangle. So here's what I mean. Instead of finding the ratio between the corresponding sides, let's find ratios of side lengths within one triangle. So let's try taking this guy divided by this guy. What do we get? To make it easier, let's call them names. Let's call this one A, let's call this one B, and we'll call this one C. What do we get when we take A divided by B? Just try that in your calculator. We get approximately 1.732. Let's try another one. Let's try B divided by C. So if we take B over C, we get 0.5 divided by 1, which is 0.5. And if we try B, let's try A divided by C. We can keep on trying them to the, and we'll get 0.8660 divided by 1, which is going to be 0.8660. Let's see if we get something similar in the bottom triangle here. So let's call this guy our C, this guy our A, and this guy our B. Let's check what A divided by B is in this triangle. So these are completely different numbers than this. So if we divide them, let's see what happens. Miraculously, we get 1.732, which is exactly what we got above when we divided A divided by B. Let's see if that was just coincidence, and let's try B over C. So if we take B over C, that would be 1.5 divided by 3, and that gives us 0.5, which is exactly the same as our ratio from above. And let's just try the last one, which is A over C. So it's going to be this ugly number divided by 3. And again, we get a matching ratio, 0.8660. So this is not a coincidence. These two, when we take the ratio of two sides in this triangle, it's going to equal the same ratios if we do the same two sides in this triangle. And that's going to happen because we have the exact same angles in this right angle triangle. So this is actually going to be true for any triangle that has 60, 30, and 90. The ratio between all of the sides are all going to be consistent in both of the triangles, or any triangle that we come up with that has 60 and 30 degrees. So to better describe relationships between the ratios of the side lengths in right angle triangles, it's going to make it so much easier if we could just give the side lengths names. And if we can give them names that everybody would agree with. So for example, in the previous example, I just put ABC. C we know is the hypotenuse, but A and B can be either side. So we're going to use more specific names. We're going to use opposite, adjacent, and hypotenuse. So hypotenuse is a familiar word to us. We know it's going to be the longest side, and it's going to be the side that's across from the right angle. Now that might seem so obvious right now because it's so clearly this is the longest side. But when we turn these triangles around, it can get very confusing which one's the hypotenuse. So always take the 90-degree angle and go across from it. That guy's hypotenuse. The last two names we have are opposite and adjacent. Now these are going to depend on what angle we're talking about, which acute angle we're talking about. Either this guy at the bottom or this guy at the top. So if we're talking about this guy at the bottom, then the opposite side is going to be opposite of the angle. It's this side length here is not touching this angle at all. It's across from the angle. which leaves us with our remaining side, which is adjacent, which means beside. It's beside the angle, but it's not hypotenuse, because hypotenuse is this long guy here. It's the other one that's beside the angle. Now I mentioned that these two sides will change depending on the angle we're talking about, because if this was our theta, then what side length would be opposite to it? Well, it would be this one. This guy would be opposite. And which side length is beside it? This one. This one would be adjacent. Hypotenuse does not change. Whether we're talking about this angle or this angle, this is still going to be the longest side, and it's still going to be across from 90 degrees. So we have more terminology that will help us describe this pattern that we found about these common ratios between similar triangles. And that's going to include these words sine, cos, and tan. So we're going to call sine, cos, and tan different ratios. So you can come up with a ratio of opposite over hypotenuse. We could divide adjacent over opposite, hypotenuse over adjacent. There's actually 6 possibilities, but we're just going to talk about 3. So we can figure out all the possibilities just from these 3. So one of the ratios is called sine, and we define that as when we take the opposite and divide it by the hypotenuse. In the previous example, I believe we called this one A and this one C, so it was like dividing A divided by C. Well, now we have proper names for it, just opposite over hypotenuse. Cosine, and short form is cos, is what we call the ratio when we divide adjacent divided by the hypotenuse. And tangent is our final ratio, and we define that as when we divide opposite over adjacent. So maybe you're thinking, well, why isn't there one for hypotenuse over adjacent? Well, there is. It's just the opposite or the reciprocal of this guy, and we do have another name for it that's related to this, but we're going to see that in a later time. So let's just focus on these 3 at first. If you're looking at this and thinking, how the heck am I going to remember that sine is the ratio that's opposite over hypotenuse? How are we going to remember those? Well, that's what Sohcahtoa is for. Sohcahtoa is just an acronym to help us remember these ratios. So if we break this down, what do you think these letters could possibly stand for? Well, S, maybe you realize, oh, that's probably just sine. It is. So the short form for sine is just S-I-N. Where would cos be? Well, cos would be right here. Here's cos, and here's tan. So how about these other leftover letters? What could they represent? Well, those are the sides. O stands for opposite, and H stands for hypotenuse. For the next one, after cos, A stands for adjacent, and H stands for hypotenuse. And lastly, after tan, we have opposite and adjacent. Notice I'm using short forms. Instead of opposite, OPP is fine. Hypotenuse, hype. Adjacent, ADJ. So let's just see if Sohcahtoa works. So sine is beside opposite and hypotenuse. And take a look. So we just read this as sine of an angle is equal to the opposite over the hypotenuse. So the ratio sine is just opposite over hypotenuse. Done. The ratio cos of a particular angle is just adjacent divided by hypotenuse. And look at that. And next, tan of a ratio is just equal to opposite over adjacent. There we go. So that's how we remember what ratio has what name. Sohcahtoa. So now that we have this fancy new terminology, sine, cosine, tangent, let's actually find the sine, cosine, tangent of different angles using the triangles that we found on the first page. So I just rewrote them. These are our 30, 60, 90 triangles. So I just rewrote them just so we can get to them easier, but you can just flip back to the first page. So let's find the sine, cos, and tan of 30 in triangle number 1, and let's find the sine, cos, and tan of 30 in triangle number 2. So first of all, what the heck is sine? Try not to flip back to the previous page. See if you can use our little trick of Sohcahtoa to help you. So we have Sohcahtoa. So we know sine is this guy here. So sine is just O over H, which is opposite over hypotenuse. So I'm just going to write that as a little reminder. Opposite side divided by the hypotenuse side. So again, instead of using ABC, we have these specific names here. So let's take a look at triangle number 1. This was our first guy that we came up with, and this was our second guy that we came up with. So we need to figure out which one's opposite. So we're talking about the angle 30 degrees. So here is our theta. So we need to think, what's opposite of this theta? Well, it's going to be across from it. Don't be confused. When we're going to use 60 degrees, this side will be across from it. But right now, here's our theta, 30 degrees. So across from it will be our opposite. So here's our opposite. By the way, we should always start with hypotenuse. We should always start with hypotenuse, which is the longest slice. Clearly this one. We have the side lengths, and also it's across from the 90 degrees. So I'm going to write that this guy is our hypotenuse. And the leftover guy must be our adjacent side, and it's right next to the 30 degrees, so this makes sense. So let's figure out what the sine of this 30 degrees or this 30 degrees is. So it would be opposite over a hypotenuse. Sorry, opposite over hypotenuse. So let's do it. 0.5 divided by 1 is just going to be 0.5. Let's try the cosine. Well, we know that cosine is just A over H because of Sohcahtoa, ka. So we have our cosine is just equal to adjacent side over hypotenuse. So let's figure out what that's going to be. So what's the cos of 30 degrees? Well, adjacent is this guy, hypotenuse is this guy, so just divide these two, and we would get 0.8660, adjacent over hypotenuse. And last, let's do tan. Tan is just going to equal opposite over adjacent. So I'm going to write opposite over adjacent. And our tan is going to be opposite, 0.5 divided by 0.8660. And we get 0.5774 approximately. So now what we can do is we could do the same thing for triangle 2 for the 30 degrees here. So here's our opposite, here's adjacent, here's our hypotenuse. But we actually already did this exercise. We show that if we divide the same, that if we find the same ratios, we're going to get the same number. So we can just check to make sure. If we take this opposite side divided by this hypotenuse, 1.5 divided by 3 will get 0.5. And if we take adjacent over hypotenuse, this guy here divided by this guy, we'll get 0.8660. So we can just copy down these ratios here. And again, if you can't remember why that's true, just take the exact same ratios, divide the same ratios in this triangle as well. So let's do our 60 degrees now. So now we want this in terms of 60 degrees. So all of our side lengths are going to change. So our side lengths are going to change. The labels that we put on the side lengths are going to change, except for one of them. Hypotenuse is still going to be hypotenuse. So hypotenuse is not going to change because it's always across from the 90 degrees and it's always the longest. But now, which one's the opposite side? If we're talking about if the angle we're looking at is 60 degrees, what's opposite to 60 degrees? Well, it's this guy over here. So I'm going to cross this guy out, and now this guy becomes our opposite. And what's left over is this guy here. This one is our adjacent side. Adjacent is right beside our angle. So let's find the sine, cos, and tan now of this 60-degree angle. So sine we know is opposite over hypotenuse. So let's take 0.8660 divided by 1. And we know we would just get 0.8660. Let's take the cosine of 60. Cosine is just adjacent over hypotenuse, so let's do it. 0.5 divided by the hypotenuse, 1. 0.5 divided by 1 is just 0.5. And last, let's take the tangent. So the tangent is opposite over adjacent, so we'll take this guy here, 0.8660 divided by 0.5, and we would get 1.732. Okay, and if we want to do it for the second triangle for 60 degrees, so this guy here, triangle number 2, so we would label, so here's our hypotenuse, oops, here's our hypotenuse, here's our opposite, here's our adjacent, and if we divide the same side lengths, so sine is equal to opposite this guy over hypotenuse, we're going to get the same numbers as we did for this other 60 degrees because we proved that in the first example. So I'm just going to copy down all of these 60 degrees from this triangle into this guy right down here. So what we found is that we can find the sine cosine tangent ratio for all of these different angles. So 30, 60 so far. We could derive 45 if we wanted to. And this is going to help us solve triangles, solve for side lengths, solve for angles. But what about all the other angle measurements? What about 41 and 57 and 72.5? How are we going to figure out those ones? So lucky for us, mathematicians before us have already found the ratios of all the angles inside of our right angle triangle. And they can be found in something called trigonometry tables. And if you scan our QR code on your worksheet, you can see these trigonometry tables. And take a look at 30 degrees and 60 degrees, and you're going to see these ratios here. So they don't just have 30 and 60 degrees, they have all the angles between 0 and 90 degrees. So also lucky for us is all of those tables are programmed right in our calculator. So if we just punch in sine of 30, we should get 0.5. And if we punch in tan of 60, we should get 0.5774. So try these on your calculator now. Be careful if you're not getting these ratios that we found in our chart, then you need to make sure that your calculator is in degree mode. It should say DEG or D at the top of your calculator. So if your calculator is working properly and it's in degree mode, you should get the following solutions. So sine of 30 is 0.5. We derived that, so it's right over here. Our sine of 30 is 0.5. And don't forget what that means. Sine of 30 just means in a triangle, right angle triangle that has 30 degrees in it, when you take the opposite over the hypotenuse and divide it, you get 0.5. Same with tan of 60. When we have a triangle with 60 degrees in it, and we take opposite over adjacent, we'll get this answer right here, and we got that over here. So tan of 60, we got it. These two we don't have triangles for, so just punch them into your calculator. All those trig tables are programmed into it. So if we had a triangle with 40 degrees in it, the adjacent side over the hypotenuse side would equal this guy. And if we had a triangle with 89 degrees in it, if we would take the opposite side over the hypotenuse side, we would get this. So when we press the sine, cosine, tan buttons in our calculator, we're finding ratios. But how about if we need to find an angle? So if we need to go backwards from the ratio and find an angle, we can do that with something called trigonometric inverse functions, or short form just trig inverse functions. So there's three, one for each trig ratio. There's sine inverse, and that looks like a sine. It looks like to the power of -1, but it's not. It implies an inverse, so an opposite. Cosine inverse, that's cos -1, and tangent inverse, tan -1. So if you take the sine of an angle, for example, it gives you a ratio. But if you take the ratio and you apply sine inverse to it, it undoes whatever sine did and brings us back to the angle. So sine inverse just undoes the sine function. Cosine inverse just undoes the cos function, and tangent inverse undoes the tan function. So they just go backwards. So let's do a quick example before we use our calculator. If we know that sine of some angle is equal to 0.5, well, we know that solution. We know the answer is supposed to be 30 degrees. We've seen that over and over and over again. So we know the answer. The answer is that theta is equal to 30 degrees. Well, because sine of 30 is equal to 0.5. How could we actually come up with this 30 degrees using our calculator? Well, think about it like we need to get theta by itself. We need to solve for theta. And so we want to undo sine. And the thing that undoes sine, or is the opposite of sine, is sine inverse. So if I were to take sine and I were to apply the opposite on the other side, it would look like theta equals, instead of sine, I would use sine inverse. Sine inverse of 0.5. And what that's asking, it's saying if the ratio is 0.5, what must have been the angle? That's what that's doing. It's undoing it. It's like filling in the blank. If we're given the answer, what was the original question? What was the angle? And if you do this guy in your calculator, you're going to get a theta value of 30 degrees. If you're wondering how to get sine inverse in your calculator, it normally appears over the sine button, and you have to press your second function button. So it's usually a colored button in your top left, and press sine, and then this sine inverse is going to appear. If you're still having trouble with it, we can go over it together in class. So try these 3 examples here, where we're given the answer, we're given the ratio. Can you find the angle? So let's take these up. So all of these are giving us the answer. Oops. Here we go. All of these are giving us the answer, so it's giving us the ratio. What was the original angle? So remember, if we want to get rid of sine, all we have to do is the opposite on the other side to undo it. So we're going to take the sine inverse of this guy and see, oh, okay, the angle must have been 70. We can check to make sure that this is right by just taking the sine of 70 degrees. Is the sine of 70 degrees equal to that? Approximately, yes it is. This guy here, we got to get rid of cos. Cos of some angle is equal to this ratio. So that means all we have to do is take cos inverse, cos -1 of that ratio, and we get 42 degrees. And last, we need to undo tan. Tan of some ratio is equal to this. So let's go opposite of tan. It's going to be tan inverse. So take the tan inverse of this guy, and we get 85 degrees. So now that we know what trigonometric ratios are, what's the sine ratio is, cosine, and tangent ratio is, we can use it to solve triangles. So to solve a triangle means to find all the side lengths and angles. So in order to use it, ask yourself these 3 questions. In an example where we're looking for a side length or an angle, figure out what are you given, what do you have, what do you need, and what should you use to find it? Because now we have 3 tools. We could use the sine ratio, the cosine ratio, or the tan ratio. So in this question, it says solve for the value of x in the following triangle. So we're not solving the entire triangle, finding all side lengths and angles, but just this one in particular. So let's start by asking ourselves with the first question, what do I have? Well, I have an angle, I have this side, and I need this side. But remember, we have a particular name for these sides, so we don't have to keep pointing to them and just saying this side. We've got special names for it, and the names are opposite, hypotenuse, and adjacent. So let's first label the hypotenuse, as we've done before. So across from the 90 degrees. And then across from the angle that we're given, or the angle that we're using, is going to be the opposite side. And here is our adjacent side. And just a final reminder, we can only use sine, cos, and tan ratios when we have a 90-degree angle in our triangle, so only in right angle triangles. So now we can better list what do we have. So instead of pointing at, we have 7. Let's call it hypotenuse. We have the hypotenuse. What else do we have? We have the angle. So let's call that angle theta. What do we need? We need the adjacent side. So we need this guy right here. So instead of calling it x, call it adjacent, because it's going to help us to pick which ratio we should use. So we need adjacent. So as long as we have one side length and an angle, we can solve for the other side length using just a sine ratio, a cosine, or a tangent ratio. The question is, which one do we want to use? So we have hypotenuse and we need adjacent, and we have the angle. So we need a ratio that involves hypotenuse and adjacent. Which one is that? So if I just quickly write out Sohcahtoa, which ratio uses hypotenuse and adjacent? So sine uses opposite and hypotenuse. Cos uses hypotenuse and adjacent. There they are. Tan uses opposite and adjacent. We don't have opposite, so we can't use it, nor do we need it. So we're going to use this ratio right here. So now that we know what ratio to use, let's set it up. We know that the cos of some angle is just equal to the ratio between the adjacent side and the hypotenuse side. That's what cos is. So let's fill in what we do know. We know parts of the pieces of the puzzle, and we can use it to find the missing piece. So we have our angle. Our angle is 39 degrees, is equal to adjacent side we don't have. So we can just call that x, and our hypotenuse is 7. So we can check what the cos of 39 is. We can check in those trig tables that we referenced before, or it's in our calculator. All of those trig tables are programmed into our calculator, so we can just punch that in the calculator. But before we do, let's get x by itself. I know I need to get rid of this divided by 7. I'm solving for this guy up here. So I know to get rid of that divided by 7, I'm just going to multiply by 7 on both sides, so that these two cancel out. And what's left is I'm going to put 7 cos of 39 into my calculator, and that's going to give me the value for x. When we plug it into our calculator, we get an x value of 5.44 approximately. So let's try another example. So again, we're going to solve for x here. So we need to figure out what do we have, what do we need, so what should we use. So start by labeling the triangle. Try that on your own and come back to the video. All right. So we have our hypotenuse across from the 90, our opposite side, which is across from the angle that we're going to use, and the leftover is our adjacent. So next, let's make our list. What do we have? What do we need? Well, we have the opposite sides. We have OPP. We have the angle, so we can call that theta. We have theta. And what do we need? We need x, which is our adjacent side. We need adjacent. Hypotenuse is not on our list because we don't have it and we don't need it either. We're just finding the x value. So take a look at these two side lengths here. Which ratio uses opposite and adjacent? Taking a look at Sohcahtoa. If you take a look at TOA, T-O-A, tan has opposite and adjacent in it. So therefore we're going to use tan. So let's set it up. We know that tan of an angle is equal to the opposite side over, or divided by the adjacent side. So let's fill it in. Tan of our angle is 40 degrees. It's equal to our opposite side is 20, and our adjacent side, we don't know, it's x. So this is very similar to the previous question, except that what we're looking for is at the bottom. So we need to solve for that x, and there's a trick to do so. We can just use cross multiplication. If we have two fractions on either side of an equal sign, then we can solve it by crisscrossing like this, multiplying from the bottom to the top and multiplying from the bottom to the top. It's called cross multiplication, and you can only use this when we have two fractions on either side of an equal sign. So how it's going to work is I'm going to multiply x times tan of 40, so it's going to make x times tan of 40 equal to 1 times 20. Cross and multiply. 1 times 20 is just 20. And so we know we can punch that into our calculator, tan of 40, or use a trig table. But let's just use a calculator once. And so to do that, let's get x by itself first, and let's divide by tan 40, which we know is just a number. Tan of 40 divided by tan of 40. So our final answer is going to be whatever 20 divided by the tan of 40 is, and all of that is programmed to our calculator. So punch this into your calculator, and we get approximately 23.84. So that must be our side length x. Let's try one last example, starting it all again. Note that we've got a right angle triangle, so we can use sine, cos, and tan. So let's start by labeling. Try labeling and making your list on your own and see if you can choose which ratio we should use. So try that now. So once we have everything labeled, we don't have an angle, but we're looking for that angle. So we're going to look in the perspective of that angle, which is why this is the opposite side and this is the adjacent side. We have the opposite side, we have the hypotenuse, and now we need theta. So taking a look at these two side lengths, what ratio involves opposite and hypotenuse? And that ratio is going to be sine. So we've got to use sine. So let's set it up together quickly. So we've got sine of an angle is equal to opposite over hypotenuse. Sine, we don't know what the angle is, theta, so let's leave theta. Okay. So we don't know what theta is, but we know what opposite is and we know what hypotenuse is. So we're going to write opposite, which is 39, and hypotenuse, which is 44. Now we can just divide those in our calculator, but let's just use the calculator once to reduce our rounding error as much as possible. We need to solve for theta. So it's like we're given the ratio, we need to find the angle. So we need to go backwards, and we learned how to do that. To get rid of sine, we're just going to put it on the other side, take the sine inverse of this ratio, and it's going to give us the angle. So we're going to write theta is equal to the sine inverse of 39 over 44, and check what that is in your calculator. And we get a theta of 62.42 approximately, and there's our angle.